then we come to our next presentation. Oh, you have a question, or?
No, I didn't know if you were introducing or me.
No, I'm introducing. Okay, we're coming to our next presentation. That's one we have in the section of security, and we might discuss that a little later, a little more, why there's only one presentation on this topic. And the presentation was originally designed by Lars Völker and Oliver Creighton, a colleague from BMW who was also part in the security department, but who's just moved to the United States starting 1st of November, so he couldn't really directly come back for this conference. And luckily, we have Tobias Hauber, who took his place, who's from the same department and also responsible for the Ethernet security at BMW. And with that, I'd like to welcome Lars from Technica Engineering and Tobias Hauber from BMW for this presentation on automotive MACsec architecture.
Perfect. Thank you, Kirsten, for the nice introduction. Yeah, let's speak about automotive MACsec architecture. Let's start also with a short, with a brief look into the history of electric and electronic functions, starting in the 70s and 80s, where we introduced the first electric and electronic functions. And due to customer demands, we have constantly increased the amount of these functions, and we also have constantly increased the complexity of these functions, which then leads to a proliferation of networking technologies. Again, here a picture from the 80s. We have a very simple network technology. And if you take a look at what we have there in 2018 or 2021, yeah, you see that we have increased a lot. We have a lot more complexity. We have multiple different network technologies in the car. They all have their dedicated use cases, and they are used at the same time. And one technology stands out. Automotive Ethernet stands out because it's well suited for almost all these onboard use cases. The reason for that is it's a converged medium. You can have all different kind of data on it. You can have audio data, you can have video data, you can have control traffic on it. And that makes it the perfect network technology for different kind of domains, like infotainment domain or the autonomous driving domain, where you need to connect a lot of sensors and actors with each other. And they have, in terms requirements to high bandwidth, they have requirements on low latency, and that just requires a modern networking technology like automotive Ethernet. And if you now think about securing all the traffic, you will hit a wall very fast, right? You will hit a wall very fast because if you start from the, if you come from the function-oriented way where we come from, where you take a look at every individual car function and do risk assessment and security analysis for all these individual functions, and you make sure that you install security measures to mitigate these risks that you have identified before, you will end up with a graph like that, and it just doesn't scale anymore. So we do have dedicated security mechanisms in place. We have IPsec, we have TLS, we have SecOC, but looking at every individual function just doesn't work anymore. And you wonder how to make it better, right? And one possibility is to just push the security one layer down, and yeah, that's the idea of MACsec. And if we take a look at the next generation architecture, you will see that the car exists out of a lot of these commodity ECUs. They have a clear function domain, and they don't change so much over time. You don't need to update them so much. That's what we like to call the rolling chassis. And on top of that, we have the custom-made components. We have, in our case, the BMW components, and they bring the competitive advantage. They are high-performance ECUs, they compute a lot of data, and they are all they all have an Ethernet connection, and they are all connected to the Ethernet backbone. And that's how we make sure that we are ready for different market changes, customer demands. We can deliver fast updates. We can deliver updates over a long time for these high-performance ECUs. And if we take a look at the architecture, it's a quite simple structure. We have the peripheral communication on the bottom and then the central communication on the top. And with that comes the idea, let's protect 100% of the traffic here. Let's make sure that all protocols, that all the traffic is 100% secure. Let's do not make the risk assessment and security analysis for every individual car function. Let's just make sure that all the traffic there is protected. And with that comes requirements, right? 3 major requirements. First is startup times. You need to be very fast starting all the components and all the functions, right? The customer is just entering the vehicle, is opening the door, takes a seat, and already expects at that point that the car is fully working. And that requires very fast boot up times for the components, and it requires also very fast startup times for the whole network technologies, including the security mechanisms. Second is energy consumption. You don't want that these complex ECUs and that these complex functions drain energy all the time. That means from a network perspective, you need to handle a network that is partially turned off, that is changing all the time, and that has to be considered as well. And the third point is scalability. You need to be able to scale up and scale down based on different customer demands, based on different market demands, and you need to be able to react also on changing customer or market demands. That's not all. Also, the manufacturing process is very challenging as well. You have in the manufacturing process, you only have a very brief time slot where the car is fully built, is turned on, and where you can do your stuff, where you can install your security keys, where you can install your certificates, where you can bind ECUs with each other, you can bind ECUs to the vehicle, and that has to happen on time, and it has to be very fast. And that brings another requirement for the production process. You need to build up and configure your security network fully automated. You need to have robust processes in place, and you also need to have a design for an untrusted environment. You cannot be sure that all the cars are built up in the same kind of plant. It can also happen that the car is built in a plant from another company, or a more prominent use case, you need to be able to handle servicing cars at third-party dealerships as well. And before I hand over to Lars, one last thought about defense in depth, because if you think what hackers are nowadays capable of, you need to have security installed on every single layer, starting from the very bottom ECU architecture up to the back-end systems. You cannot just rely on security on your network technology. You have to install security in every single layer. But we need to have a very robust security mechanism in our Ethernet backbone. That is what MACsec needs to be in the future. And how that works is Lars telling you now. Perfect.
Thanks, Tobias. So for my part, I will go into the ECU architecture, so basically picking up the requirements and ideas Tobias presented us and show how you implement them and what's the right way to get that working. So I brought you a very simple architecture picture of an ECU to get us started, and I'm pretty sure you all know that already, right? So I will be very fast. There will be some applications running there because, you don't need the ECU without applications. Then you, of course, have some media-dependent interface, and we all assume that's Ethernet here, I guess. And then some parts in between, like a PHY and a Mac controller in your SoC or a microcontroller. Then you have probably some MII between them or something different now these days. And then of course you have some stack on them running in software. Layer 2, like maybe VLANs and certain QS mechanisms, but then also going up to like the application layer protocols, for instance, some IP or diagnostics over IP. What we have here new is now, of course, we have this little star in the middle, which is our MACsec key agreement protocol, or key agreement. And that, of course, needs some keys. And what we want to figure out now in the next few minutes is how do we do that, right? Where do you put all the parts and how does that fit together? So where's MACsec in here? Oh, I didn't show it because there are too many options. The first one would be you put it in the PHY. And that's really wonderful because it's very fast to implement. Because we have a lot of good semiconductor vendors that have done a very good job in bringing us the innovations we needed, and MACsec is one of them right now being rolled out, and so that's a perfect place. If you talk to some people, of course, they say like, hold on, your security ends in the first chip, right, in the ECU. So what about the MI now? It's not protected, right? Everything is unprotected there. And I would typically answer, yeah, sure, but you cannot industrialize this kind of attack. So it's, for many, many use cases, not a problem at all, because how could you attack that? It's some PCB lines which can be hidden and have some physical security on the ECU as well. So, but if you need more, then we can go for the Mac controller, right? It's MACsec. The name already says that you can put it in the Mac. And if you do that, of course, then the MI lines are not unprotected anymore. And the cool thing is then you're more secure, I guess. The thing now is that we have a lot of microcontrollers. We have a lot of SoCs, so maybe your favorite SoC or microcontroller does not have MACsec support quite yet, and you have to wait a couple of years. So for the short term, might not be the best solution, but yeah, if you have it there, it's perfectly fine. And then of course the last solution, especially if you have like very small bandwidth, like 100 megabit or below, then of course doing it in software is probably a solution as well. If you think about today's crypto acceleration and typical microcontrollers and SoCs, it's easily done, right? Up to 100 megabits of protection with low latency is possible on the right microcontrollers and SoCs. So that's a very simple ECU, isn't it? We might want to do it a little bit more complicated. And then look now at ECUs with having an Ethernet switch in the middle. So how do you do it now? So the thing with MACsec is what we envision is like a point-to-point kind of protection. So in order to cover every communication, like every protocol, except maybe the MKA itself, what you want to do is you want to have a point-to-point MACsec implementation. So your PHY, here it's an integrated PHY, if you see in the lower left part of the picture, that will be protecting everything on the wire. In order to do that, of course, we have to run the MKA now not only for one port, but for multiple ports. And what you can see in the middle, I gave now the internal core of the switch, the MKA, as a job. And in addition, we get like 3 long-term secrets, those connectivity association keys, CAKs you see in the middle in yellow. So now from those, the bottom 3 links would be protected. We could, of course, run the MKA also on the microcontroller SoC if you want to. And then, of course, you would have to basically push the keys via something like the MDIO or a SPI or something into the switch in order to install then the session keys you need. Or you could use both. Why would you do both? One simple solution would be, for instance, that you run on your internal MI between the SoC and your Ethernet switch you want to run. Also MACsec, because they have a very, very high security use case, and you don't want to take a risk that maybe someone can take your ECU apart. So that's one possibility. You can go there as well. And we are missing one thing at the top. There's a single PHY which doesn't have MACsec, and while you can, of course, get a PHY with MACsec integrated, you could also have maybe a switch with a MAC port on an MI which already have the MACsec built in, and then the PHY at the top could be, for instance, without MACsec as well. So many, many options we can use. And what you have seen, well, added parts and parts, the number of keys, of course, we need in a switch increased as well, right? Because for every port, we want a different key in order to make sure that if there's an attack, we are not breaking everything at once. So what do we want to add now, right? MACsec is one part, but is that enough? Tobias told us that defense in depth is really important, so you want to add some complementary parts in order to make sure that everything works out fine. And one thing I would add as the first thing would be filtering in the switch. So if you start filtering in the switch on every port, you can make sure that something like IP address spoofing is not possible anymore. I mean, you have to think about it, right? I authenticate very strongly the ECU on the other part of the Ethernet cable. And I can know the IP address of that. So why don't I filter that? That every message coming from that ECU can only come from the certain IP address. So IP address spoofing, of course, then is not a thing anymore. And I can, of course, do this for instance, for MAC addresses and other things as well. So adding strong filtering, always a good idea. So if I add that, so you know my background maybe, I'm more coming from the application layer protocols in the beginning. So I would add something on that top of that again, right? So I would add ACLs, access control lists. If you think about some IP, for instance, or other service-based communication protocols, it's very hard to protect every service and every access to the service, right? But now, if I have the IP spoofing, you know, not as a problem anymore, and I know the identity of the sender of every packet, it's very simple now to get those kind of features implemented, because now I can go ahead and say, like, you know, that's the IP address. I know who that is because I cannot spoof it anymore. So I know if that ECU can now access the service or cannot access the service, or if it can offer the service or not offer the service. So that's the second part. You probably want to add, because now you know already the security started with MACsec and the MK at the bottom, now starts to spill out in other protocols and make them stronger as well. And then, of course, at the end, you might have some use cases like car immobilizer or mileage protection. And for those, you want to make sure that for your security concept, they are as strong as possible, right? Because they're like really important for your type approval, for the customer satisfaction. So maybe in some cases, it makes total sense to add like a second security layer. And that would be, for instance, an application-based security protocol. SecOC would be one example for that, but I know that there are many other solutions out there, but people invented, and it is fine, right? So you add that on top, and if, in the case something breaks, you have two layers. If one of them breaks, the other is still protecting everything. You're totally fine. The car can stay with the customer. You don't have to do anything. So that would be one big advantage of having defense in depth here. But then there's another thing. Tobias told us that production is very hard. Like, you know, every minute another secure network has to be automatically produced, and you have to do this in a really nice fashion. So how do you do that? And at the bottom, I tried to show you a very small abstraction of the problem. You have something called a tester. That is like a computer wants to install the keys. And in that case, you have somewhat an internal network in the car. What that looks like does not really matter too much. But what we have to do is we have to install the keys into MACsec. Because MACsec does not accept the Ethernet communication until it has the keys to start up, you know, secure communication. We have kind of a chicken egg problem here. We want to install the keys, but we cannot communicate until the keys are installed. So how do you do that? And one easy way to do that, for instance, is to bypass for certain communications the one you need to install the key actually, and it could be diagnostics, for instance, the MACsec, and make sure that you filter out those kind of communication, you know, that MACsec does not block them when it's not running, and then MACsec can protect everything else then later on as soon as the key exchange is through. So that is kind of a difference with if you look at other industries like IT industries, and that's why one of the important things when you bring in MACsec into your architecture, you need to make sure that the semiconductors reflect such different approaches, especially the way that keys are provisioned into ECUs. So if we make this now a little bit more complicated again, we come to an ECU that uses switches inside, or one switch in here in this case, right? And we now have to install multiple keys. If I want to do this with the saying like I bypass the traffic now for the diagnostics, I end up on the microcontroller on the right-hand side. So I need the keys on the left-hand side, right, and the switch. How do I do that? And if you want to protect it, and I think since those are long-term keys, you should really think about protecting that. And one simple solution would be you have like a secure exchange between those two cores. You see this black arrow at the bottom, which I typically recommend that in the tier 1 production, what you will do, you bind those two cores together cryptographically by having like an even anonymous Diffie-Hellman exchange. You have then a shared key and can have a protected, secure communication channel between those two parts. So if now the keys are coming into the diagnostic stack and the diagnostic application, you have probably then encrypted. You will then decrypt them, you know, unprotect them, and then use this secure channel to install them in the switch. So as soon as they're on the switch, you can then start MACsec and everything works out fine. So even with the switch and a microcontroller split up here, and even if you don't want to protect the MI or don't need to protect the MI, you can still build a wonderful model where everything is secure and you start up a secure as well. If we add another ECU to that on the top, behind that switch, or replace one, especially if you think about the service use case, then of course, if we use this idea of a bypass VLAN where we have an unprotected VLAN for the diagnostics and key installations, if the switch is like forwarding that, it's not a big deal, right? Very simple. Those messages go through the switch, go up to the ECU on top, and everything is fine. So I think we are here that, and at a stage that we can say that all the very important use cases and requirements have been thought through. We think everything works. We see this also on the first prototypes and implementations. So what else do you have to do? I already said prototyping is always a good idea. Prove your concept. Like prototypes, A samples, and then probably go on for ECU production. Make sure that your ideas really work. The second thing, of course, is if you then want to go further on towards the SOP, you need to do something about testing. I think testing the MKA is one of the most important parts. It's a software-based implementation. It's not so simple, but it's not so difficult that you cannot get it right. So a good set of testing tools and test cases usually helps a lot there. Same goes, by the way, for the MACsec itself. And since that is a semiconductor block typically, you probably have to test it very early, so making sure that the semiconductors are all fine. And looks good right now. And the last aspect I will cover only very slightly because we have discussed this last year a little bit. There is the thing of trace analysis, right? You have all your test cars, the whole fleet out there collecting data for you. And you want to make sure that while MACsec is turned on, you can still analyze all your data and find all the bugs on the higher level protocols and also on your application implementations, right? So if you do, for instance, authentication only MACsec, that's pretty simple, right? You just have to record the messages on Ethernet, for which we, for instance, offer tools. And then with that traces coming out, you can, for instance, use Wireshark. And I think I told that last year that we also have patched Wireshark in order that you can see like authentication only MACsec and analyze like some IP on top of that, for instance. So with that point being said, we come to the summary. And I think the good news are MACsec is pretty much ready for you to design it into a car. The E architecture that employs MACsec is clearly understood. We know how to build the ECU architecture with MACsec inside it. We know that we can bring up MACsec very, very fast and robust. Our implementers have just told me the other day that they are now with the key exchange for MACsec round about at 10 milliseconds on an automotive platform. So that's much faster than TLS or IPsec will ever be. So really fast coming up, everything is fine, and with the hardware-based support, no matter what your line speed is, you can protect that, right? So very high performance and security at the same time. What you need to make sure that the MKA implementation, your key agreement, is fast enough, that is automotive qualified. I gave a talk like 3 or 4 months ago where I explained exactly how to do that, because if you know the standard says key exchange can take up to 8 seconds, we want 10 milliseconds or 20, something like that. So there's quite some changes you have to do. We have some good ideas how to do that and have proven that in code. And then, of course, like I said, prototyping is always a good idea. So there's one open question we have left. Is there any interest in creating like an automotive profile for MACsec? If that is the case, then maybe you want to contact Tobias and me later on and then see if we can go forward with that. I bet Max will help us with the IEEE work there as well. So let's see how that will go, how we figure that out. So thanks everyone, and maybe we have a question or two.
Thank you, Lars and Tobias. So are there any questions from anybody? If anybody in the audience has some, please go to the back. I have a question to you two first. That might be a little, I don't know whether it's surprising or not, but when we actually selected the presentations, you get a number of presentations coming in and we sort of sort them by topics. We actually had very, very few presentations covering the topic of security, automotive security. We had a lot of other tech days we always had some presentations on security and we had people applying for it, but this time it was really very, very few. So do you have any explanation? Would you say most of it is already solved, or or because Ethernet provides these protocols that you can select, or is it too early, or is it too late, or why is it suddenly that it has so little to discuss, maybe? Yeah?
I think it's definitely not solved yet. I think we're starting right now, and MACsec is a very important step. Well, I think the OEMs and the companies are changing their thinking about that right now, or there is a process happening right now, and yeah, from my point of view, it's just still at the very beginning. We're still very early in discussing security topics in the automotive industry.
Okay. Then Martin, you have a question?
Yes, thanks for the nice presentation. I have one question. So a hardware implementation of a security mechanism, of course, has a lot of advantages, as you pointed out. But my question is, how do you know it's not hacked? And if it is hacked, then you cannot update it. So I think that's always the risk of a hardware implementation.
Yeah, that's a good question. So how do I know that the hardware implementation isn't hacked? So the question is, of course, what do you mean by hacked, right? So typically what you see on the ECUs, you see that someone gains control over certain parts of it. And that's typically on a microcontroller or microprocessor, right? So if you have like this hardware-based MACsec block, that of course cannot happen, right? It's like a crypto block and a very simple block with that. So I would say that on the complexity that block has, like almost all the typically known attacks won't be happening, right? You cannot do like a buffer overflow or something if there are no buffers and software behind that. So I'm pretty confident that the semiconductor vendors know what they are doing, and they're not putting in there like an ARM core or something and then put the MACsec on the ARM core and think that's the best solution, right? But it's a very hardware-based solution. You can get that right if you know what you're doing.
Okay.
Okay, thank you.
Thank you very much.
We have a question online.
We actually have 3 online questions.
Oh, we have 3 online
that have
questions.
come in already.
Okay, we need to rush then.
Yeah, so the first one comes from David Fuchs asking about what about the cooperation with AUTOSAR consortium related to the MACsec?
I can answer that. Yes, of course. AUTOSAR and MACsec is of course very important to put both together. There were some first steps being undertaken. I think Alex, as your colleague, started a lot of discussions there, and we are currently in the discussion how we can further enhance that topic in AUTOSAR. The current standard just came out, right? So that's too late. So it's next year's standard where we try to push something in, and it's, of course, you always need a couple of months to do that. So we are quite hopeful that for next year we will add some cool ideas there and concepts so you can implement it in AUTOSAR.
Mm-hmm.
All right. The next question comes from Giuseppe Tofinicchio. What are the main challenges in extending MACsec security scope from point to point to end to end?
I take that? Okay. So my personal opinion is that point to point is much easier to do, right? Because you can protect everything except the MKA, of course, and maybe the way to bring in the keys. If you do like end-to-end MACsec, you basically fall back to something very similar to IPsec, right? From the model and security is very similar. And the problem you're getting into is that the large amount of multicast and broadcast data in the car, I mean, we transfer a lot of data of like sensors in the car. So those are often, or like let's think about radar, laser scanner, or audio or video. You often want to use multicast for that. And if you use like a more end-to-end approach for MACsec, of course, you lose the very interesting capability of making it very easy to protect everything, no matter if it's unicast, multicast, or broadcast, and every protocol on top of layer 2. So in a like an end-to-end scenario, you will lose that, and you can stick with then IPsec or something, right?
We have a question from Hari Pamar. Where do you think the automotive profile definition can take place? In IEEE, Open Alliance, or AUTOSAR, or all?
I would prefer not to have all of them taking place. I think it's probably IEEE, right? I mean, my understanding would be IEEE would make sense, but we will see. I think that's something we would ask Max to help us with, because for TSN, I think he knows how to do it. So we'll create the right profile, so I'm trusting in Max, right?
And I think since we're running out of time, there is one more that just came in again from Giuseppe. In which use cases does IPsec have advantages over MACsec?
Do you have an idea?
Yeah, if we think about MACsec as hop to hop, then of course IPsec is end to end more or less. But rather than that,
I think there's one advantage. You can already start it right now, right? On the old chip, it already works. That's, I think, the main advantage. So you already have it, you can use it. MACsec is something for the next years to be used.
And
So
IPsec might work on the multi-drop link.
I thought we want to make MACsec work on the multi-drop as well.
Yeah, we are, but you can use IPsec there now today.
Yeah.
Okay, then thank you very much once more for your
Thank you.
very interesting presentation.